Today we're talking about integration. We're talking about a method to integrate a problem. Okay, so if we want to integrate, and it's not just as easy as using kind of that power rule where we increase the power by 1 and then kind of divide the coefficient by that power and plus c and all that sort of stuff. If it's not just as simple as that, and you found that well, maybe it's not just as simple with some of the functions, that U-substitution is the first major method of integration that we're going to learn in calculus. Now, there are lots of methods of integration that will help you with more difficult functions. This is the first level, okay? And if you pay very close attention here, this is going to make things easier. But there's a few things that you need to keep in mind. So first of all, let's just back up a little bit. And remember that when we are differentiating a function, okay, so for example, when we take the derivative of sine of x, what's the derivative of sine? It is cos of x. That's really easy, right? The derivative of sine is cos. Now, notice that if I wanted to go backwards from this to sine of x, I would have to integrate, right? So first of all, we need to understand that going one way, differentiating one way is differentiating. The other way, going back from that, is integrating. Now, if we're only given cos of x, we can find the integral of cos of x, first of all, by finding the antiderivative of this function. Remember that? So this is all chapter 9 stuff. Antiderivative of cos of x is sine of x. The only problem is that we don't really know if there was a constant there as well, because remember, when we differentiate sine, we get cos, but when we differentiate a constant, we would get 0, and it wouldn't show up over here. It wouldn't be here. So what do we have to put over here when we integrate? Plus c, so plus some possible unknown constant. Okay, so that's the one thing we have to remember. So the tricky part becomes, okay, when we're asked to integrate some maybe more complicated functions. Now, we know this one probably from, I think you guys have done a question like this already. You just used intuition and what you know about the chain rule, undoing the chain rule, right? So U-substitution helps us with undoing the chain rule, okay? So the integral of 3 cos of 3x is sine of 3x. Because if I were to take the derivative of sine of 3x, I would get 3 cos 3x due to the chain rule. So we're going to take a little bit of the mystery out of this integration by doing U-substitution. So this is going to become more methodical, and I'm going to show you what the method is to doing this. So you've copied this out already previous to us starting this lesson. But I want to just go over it real quickly with you. Okay, so integrating by this method called U-substitution is a good method when you see the derivative of an inner function as well as a part of the original function, or as a part of the original function. So what you see is you see some function and its derivative at the same time. When you see both those things, it's a good idea to do U-substitution. So let's go back up here and take a look at this previous example. What I see here, okay, for 3 cos 3x, I see a function of cos of 3x, but I also see an inner function of 3x. Do you guys see that? So the inner function is important. If you see a derivative, the derivative of that inner function or part of the derivative, then like the 3 is the derivative actually for 3x, right? So when you see an inner function and its derivative all contained together in there, that should make you clue in and say, hey, we can maybe do U-substitution. So let me give you, let's go to the next step here and let's actually do some examples. And we'll do this example first, and I'll show you how to approach this. So let's do this. Instead of using just intuition, let's use U-substitution. I'll show you how it works. So, with this particular problem, and I realize this may be covered a bit, So with this particular problem right here, the u is going to be what the inner function is, okay? The inner function. You may have an outer function and an inner function. U is going to be the inner function. And what this really is taking a complicated or more complicated function like 3x, or maybe 3x squared plus 2, or 4x squared minus 5x minus 1, taking that more complicated function and collapsing it into something that's really simple like a u, like a substitute variable, okay? All right, so the inner function here that we see is 3x. So for u, I'm going to let u equal 3x. Okay, that's the first step, identifying the inner function, because I do see its derivative right here. That's good news. And now what I want to do is I want to find out what the derivative of this u is with respect to x. So the derivative of u with respect to x is 3. Can we agree on that? Okay. Now, this is going to seem a little bit fishy, but this du over dx is not really a division, but in U-substitution we can kind of treat it like a ratio. And what that means is that this du over dx equals 3. The du by itself could be expressed as 3 times dx, or 3 times the little differential of x. So in a sense, this dx can be sort of multiplied by the 3, okay? So this is going to help us to do this U-substitution. So this is a little, just a little part of it that's like, this isn't a ratio, but in a sense it sort of is. So you'll see how this is going to work in a minute. All right. So I'm going to use yellow now, and over here, what I'm going to do is I'm going to write, instead of this integral with respect to x, I want to write this integral, if I can, with respect to u. I want to have a u function du. So I want to have an integral with some kind of function containing u and a du at the end. So look at this here. I can substitute 3x for u, I know that, and dx right here is equal to du when I have a 3 multiplied in front of it. So du is actually 3 times dx. So I'm going to rewrite this and I want you to watch. So if I rewrote this as cos of 3x times 3 dx, do you see how this 3 dx I have as a complete unit right here? So I can actually now substitute u in, and we have a complete integral. So I have now cos of u du. So notice how I've gone from with respect to x, integrating with respect to x, there's an x, and here's a dx. Now I'm integrating with respect to u. I've just had to be careful how I do my little steps here, okay? In translating this to a u, I have to be careful that I have everything accounted for. Now this one does work out pretty slick, okay? It works out pretty nicely. They're not all going to be quite this easy, but in order for you to learn this, this is a really great intermediate step. So now that I have this, do you see how cos of u, taking the integral of cos of u, is actually quite a bit easier than taking the integral of 3 cos 3x. It just makes it a little simpler. And this is an integral that we know right away. So this actually, if I now integrate, this is actually sine of u plus c. Okay? So I'm taking the integral of this function with respect to u, and that's good because I have this in terms of u, and so now I can just rewrite it as sine of u plus c. So of course the question was asking for the integral of 3 cos 3x with respect to x, so I can't leave this u as my final answer. It's just a substitution that I use to make the inner part of the question a little bit easier. Now I want to substitute back in, so watch what I do now. So now I take this u and I say, oh, what is u? Oh, u is 3x. Oh, okay. So this u gets substituted back in as 3x plus c. And there's really nothing else to do. I'm done. And as we looked at before in the intro, that of course sine of 3x is the integral of 3 cos 3x. But we kind of get tripped up with all this stuff, right? Well, now with U-substitution, we don't have to. So that's your first look at U-substitution. Let's take a look at a bunch more examples, okay? So let's do a bunch more examples here. So please copy this one down into your notes, and we'll do 3 or 4 of these examples like this. Okay, so as we look at this example, again, what we want to take a look at is this is my function here, right? This is really my function. It's this times 3. Now, I've written the 3 over here with the dx to make this the second step a little bit easier. But you could see this as 3 times 3x minus 2 all to the power of 4. And you have to do the integral of that. Okay, well, there was a chain rule, there was a power rule, a chain rule, all this mixed up. U-substitution is going to be a good idea because I see that I have an outer function right here of something to the power of 4. My inner function is 3x minus 2. So if that's my inner function, okay, then I see that I also have the derivative of that inner function as part of this overall function. So this is good news. So you're going to be able to use this, use U-substitution here. So you want to take a look at what is the inner function, and that is 3x minus 2. Well, what's the derivative of u with respect to x? Well, that is 3 dx. So again, the inner function, the innermost function, is going to be your u. You want to find the derivative and write that in terms of x. So du is the derivative of u right here with respect to x is 3 dx. Now, notice I do have 3 dx here. That's great. So this is going to become du. Everyone see that? And I'm going to be able to integrate with respect to u because I can now easily write this outer function in terms of u. Well, 3x minus 2 is u, so this becomes u to the 4th. And notice how much easier this integral is to integrate because the antiderivative of u to the 4th is super easy to write, right? So that's the whole point. We want to do some substitution so that we have an easy integral to evaluate. Okay, so let's go to, what color should I use now? Let's go to darker blue. So what's the integral of u to the 4 du? Well, 1 over 5 u to the 5 plus c. Okay, plus the chair. Don't trip over the chair. Okay, so now I substitute back because look at, I've done the integration. You see, this is the heavy lifting right here. I've gone from an integral to an evaluation of that integral. Now, the smaller part of this is I have to resubstitute my original x function in for the u. And because the dx is already taken care of because I've had this little 3 and all this, so it's all legit. Okay? So this is 1/5 3x to the minus 2 to the power of 5 plus c. It would be a good idea for you when you're first starting out here is to check this. So let's differentiate dx of this 3x minus 2 all to the 5 plus c. Let's take the derivative of this, right? And see what we get. Well, the derivative of this is going to be, we're going to have a 5 here. This is going to be 3x to the negative 2 to the power of 4. And I'm going to multiply this by what? I'm going to multiply this by 3. No, I'm differentiating this. So I bring the 5 down there. I'm differentiating this. Okay? And then plus 0. Oh, 1/5. Thank you. There's a 1/5 here. Is that what you said, 1/5? Or the 5? Okay. Yeah, I'm missing the 1/5, so thank you. I want to take the derivative of, yes, I just missed putting that in. Thank you. 1/5, because this is our function. All right? So now 1/5 times 5 is going to just give us a 1, and this is going to be then 3x minus 2 to the power of 4 times 3, or 3 times 3x minus 2 to the power of 4, and which is what we see. in the original integral right here. Yeah. Okay, so if you check that out, this is your answer. So here is your final answer, and we've checked that out. Okay, thanks for noticing that 1/5. Okay, any questions? All right, let's do another one. Let's do another one. Again, this should be pretty easy. And actually, what I'm going to maybe get you guys to do is I'm going to see if you can do this one on your own. So just take 1 minute. If you get stuck, I'll show you I'll go through this with you in 1 minute. But why don't you write this down and see if you can do this example just like we did the first two. All right, so let's do this one. Now you could multiply this in, but I don't want you to multiply this in because we're working on this U-substitution. So this one should be fairly easy. U, okay, an inner function here. Well, that's like an inner function because I see that the derivative of this inner function is also present here, right here. So let's say that the U is, and just sorry, going to move this down so you can see this. The U is going to be x squared plus 7. And du is going to be 2x dx. Everybody good with that? Yep. All right. So I see an inner function here. Now maybe there could have been an exponent there to make this a little bit more looking like an inner function, but that's okay. But I have 2x dx, which is great. So I can rewrite this as an integral as just u right here. This is u. And then since I have 2x times dx, that's exactly what du is. So I just have the integral of u du. Now this is a really easy integral to solve. So what's the integral of u? 1/2, very good, u squared plus c. And so I substitute now back in my x squared plus 7, and I'm going to see that this should be now the integral for this thing right here. If I were to integrate this, squared, thank you. If I were to integrate this now, I should get back my original statement here, my original function. So let's just do that. So if I take the derivative, that's going to be 2, okay, times 1/2 times x squared plus 7 to the power of 1, because I'm going to subtract 1 from there. And then the derivative of a constant would be 0. So I would have, times 2x here, the derivative of the inner function, and I would have 2 times 1/2 is just 1, so that's x squared plus 7 times 2x, and that is what I see here in my original question. Okay? So this is your solution there. Okay? U-substitution. Any questions? Okay. All right. Let's do another one. Copy this one out. We encounter a new slight snag with this one. Not a problem, but just a slight snag. And we're going to have to know how to get around this as well. So copy this question out, and then we'll take a look. Okay, if you had a chance to copy this out, so let's take a look here. So it looks like I have an outer function of blank, some blob to the power of 4. The inner function would be 3x minus 2 there, right? So that's my inner function. Now, I don't actually see the derivative for this inner function in this. Now, is that a problem? Well, when the derivative is simply a constant, a multiplier, that's okay. If you're missing an x, that's a bit of an issue. But if you're missing just a number like 3, right, that's all we're missing is 3. That's the derivative of this, 3. We can get around that. Let me show you how to do that. So we'll go about our business here. 3x minus 2 is u. Du is 3 dx. Now, I do not have a 3 as a constant multiplier here. I just have 1 dx. But remember, with the properties of integrals, I can actually do this. I can actually put a 3 in here as long as I put a 1/3 as a multiplier there. So 1/3 times 3 is equal to 1. So you can multiply anything by 1 without changing it. Now, it's a little bit of fancy footwork here, but I can put a 3 inside this derivative if I also put a 1/3 times the 3 in there. The 1/3 is now going to be treated as just a constant multiplier. And the properties of integrals say that if you have, remember this one, c f of x dx, that's the same as c times the integral of f of x dx. Remember that one? So that's a property, and this is really what I've done. I don't want the 1/3 in there. I want it out here. So that's no problem. So now I have, let's change colors here. Now I have my 3 dx, which is exactly what I need to replace with du. This function now is u to the 4th. And I have the integral. I can't forget my 1/3 out there, times the integral. So you can get around a missing constant multiplier by simply, you can put the multiplier in there as long as you multiply by 1 over that same multiplier, and that can be brought out of the integral. So now look what I have. I have 1/3 times, what's the integral of u to the 4th du? Well, it's the same as the antiderivative of u to the 4th, which is 1/5 u to the 5 plus c. Are we good there? So this is actually 1 over, look at this, 1/3 times 1/5. That's 1 over 15 u to the 5 plus c. If I substitute that back in, that becomes 1 over 15 times 3x minus 2 to the power of 5 plus c. And are we good with that? Did I miss anything?
Shouldn't c be c over 3 actually? Because 0 to...
Okay, well, good question, good question. So the question was, shouldn't c be actually c over 3? Now remember, c is an unknown constant. So whether it's c or 3c, it's still a constant. So yes, I see what you're saying, but in calculus, with this just c, okay, if I take c and I divide it by 3, it's still a constant, just a constant. So for our purposes here, c and c divided by 3 mean the same thing. Okay, it's still just a constant. So yes, I like your thinking. Should we have this, 1/3, right? This really, there's brackets there, right? Yes, I like it. I like your thinking. But c over 3 is still just a constant. Okay? So this constant is not important to us, really, the value. It's just saying that it's some constant. Okay? All right? Good question. Good question. I hope you're okay with the answer. Because this is going to come up many times in the future as well. Right. Next semester, this will come up in our advanced calculus. Okay. Now if I took the derivative of this, let's see, derivative of this right here, well, I get what? I get 5 over 15 times 3x minus 2 to the power of 4. Is that the same as, let's see, that's 1/3, 3x minus 2, what am I missing? Times 3. Very good. Times 3. So I have 1/3 now, times 3 is 3x minus 2 to the power of 4. Is that what I started off with? It is. Okay? So yeah, don't forget your train rule. So we're good to go. So this is the solution right here. Everyone see that? Okay. All right, you guys are doing great. You're doing great. So this one is another one that's very similar. Okay. Why don't you try this one on your own? Take a minute. Try this one on your own using U-Substitution. It's going to have the same wrinkle as the last one. So take a minute and give that one a shot. All right, hopefully you've all had a chance to do this one. Let's take a quick look here. So outside function appears to be this right here. Inner function appears to be this. I have a portion of the derivative of this inner function, 2x. I have a portion of that right here. It's only missing a constant multiplier. Good to go. This is great. U-substitution, my favorite. All right, so u is going to be x squared minus 1. Du, with respect to x, is going to be 2x dx. We good? Okay. I see that I have an x dx. I do not have a 2x dx. So I'm okay to do this. I'm going to put a 2 there as long as I put a 1/2 out front. Now I have 2x dx. You see that? So I can rewrite this integral totally in terms of u. I'm going to write 1/2 integral of, well, this is going to be u cubed, and 2x dx is actually 100% equal to du. All right, so just with this one little change out here, I've been able to write this in terms of u. It's a much simpler function to take the antiderivative of. So now this is going to be 1/2 times, what's the evaluation of this? Well, that's going to be 1/4 u to the 4th, so look right, plus c. So add 1 divided by that, okay. So then we have 1/8 u to the 4th plus c. If I substitute back in now, I have 1/8 times x squared minus 1 to the power of 4 plus c. If I take the derivative of this, what's the derivative of this equal? Well, that's going to equal 1/8. The 4 is going to come down, and we're going to have x squared minus 1 to the power of 3 plus derivative constant is 0. So that's going to be 1/2. Oh, I missed the 2x again. My goodness. 1/2 times 2x times x squared minus 1 to the power of 3. So that's going to cancel out. We're going to have x squared minus 1 cubed, and that's what I originally had. Okay?
So
Question.
what if you were missing like 2x? Would you put like 1/2x?
If you were missing the x, that presents a bit of a problem. Yeah, if you were missing the x altogether and you needed to manufacture a 2x, that's a bit of a problem. We're going to have to do that a bit of a different way. That's not a good candidate for U-substitution at this point. You're going to get questions mainly like this. Okay? All right. Okay, let's do a couple more examples. We're starting to run out of time, so I'm going to go through these with you. We've got 2 more examples that are a little bit more complicated because they've got trig functions in them. So we'll do 2 more, and then you'll be able to launch into your assignment. Okay. So the inner function. Now, please don't say that the inner function is cos of 4x because this is the outer function. Inner function is 4x. Okay. So inner function is 4x. The derivative of this inner function is 4 dx. I do not have a 4 as a multiplier in here, so what I'm going to have to do is I'm going to write 4 dx there with a 1/4 out here. Okay, not equals yet. Try not to write an equal sign until you're evaluating your integral, okay? So we've got 1/4 here. Now I can rewrite this in terms of u and this in terms of u. So I have an integral of cos of what? U times du, or cos of u du. So now I have an integral in terms of du, and I have the function in terms of u. So now you can integrate. So this is actually 1/4 times the integral of cos is sine u, okay, plus c. Now I substitute back in my 4x, so I've got sine of 4x plus c. That appears to be my solution. If I were to take the derivative of that, let's just double check that. Derivative. Okay, so the derivative of this would be 1/4. Derivative of sine is cos, so that's cos of 4x times the derivative of 4x is times 4 plus, not plus c. Wow, plus 0, which is the derivative of the constant. So 4 over times 1/4 is just 1. So we have cos of 4x. And that's what we started with in here. Good? Okay, good. I just want to give you lots of examples here so you can see. All right, one final example. Let's bring the boom here. Okay, so I've given you a little bit of a start here already on this. But if you have something like this where you have secant squared of 6x plus 1, don't panic. Okay, don't panic. Because remember, we do not need to have the derivative of the outer function present, only the derivative of what would be the inner function in order to substitute and do U-substitution. So the inner function is 6x plus 1. The derivative of the inner function is simply 6x, or 6 dx. So I do not have a 60x, but that's easy to integrate in there. No, I shouldn't use that word integrate. It's easy to put in there. So I'm going to put a 6 in there, and I'm going to put a 1/6 outside. Okay? So I'm going to rewrite this now as 1/6 times the integral of secant squared of u times du. Now I can evaluate the integral. Who remembers what the integral of secant squared is? It's tan. So we've got tan of u plus c. 1/6 tan u plus c, because tan is the integral of secant squared. Or if you take the derivative of tan, you get secant squared. So we resubstitute now 1/6 tan of 6x plus 1 plus c, and that should be our answer. And again, I'll take the derivative of this. So the derivative of 1/6 tan of 6x plus 1 is going to be what? 1/6 secant squared of 6x plus 1 times the derivative of the inner function, which is 6, plus the derivative of a constant, which is 0. 6 over 1/6 should leave us just with secant squared of 6x plus 1. So that is a good check. That's what we started with. So here is your solution. All right? U-substitution. You good? You know that so far? Okay. So there's your lesson on U-substitution. There's a bunch of examples. Again, if you see an inner function and part of its derivative, or at least the variable part of its derivative present, good candidate for U-substitution. Okay. All right. Here's just a quick look at one more example that we did. So as I get your assignment together, you can take a look at this example. Okay, there is your suggested assignment from the textbook. I say suggested because I'm not making you do any of this, but I'll give you some credit if you do it and submit it. So I'll see if I can find that in the textbook here for you. Oh, come on now. Come on. Oh, there we go. Okay. Oops. Oh, it's not happy with me today. Okay, so there's some questions from 11.3, and yeah, I'll suggest you work on those today.
And then recommend both of these as well.
Oh, sucked.